All right, guys, these are the review problems for chapter 5. First one, number 1, you were asked to estimate L4 and M4 on the interval from 0 to 4. So I'm going to get this picture up on the screen so that we can estimate because we're using it to come up with these different values. So figure shown in figure 1 as it says, so that's this one right here. So L4 means you're supposed to be using a left Riemann sum, splitting it up into 4 equal subintervals. So I'm going to mark right on here with my pencil. So if you split 1, 2, 3, and 4, so it turns it into 4 rectangles, and then you're supposed to be using the height of the left endpoint for this first one. So here's the left endpoint, this one ends up going over, and this one's under. So we've got these different widths, and I'm gonna write, let's see if I can squeeze them both on the screen. There we go. So L4, our first rectangle has a width of 1, they all do. And then the height for this one, if we're just kind of estimating, if this is 1, then I'd say that's about 0.3, that height. And then plus 1 for the next rectangle, this height is exactly on 1. Plus, and then 1 for the third rectangle, this height is right at 2.5. Plus, and then 1 for this fourth rectangle, this height is right at 2. So since they're all just multiplying by 1, we're just adding these together. So 0.3 plus 1 is 1.3, plus 2.5 is 3.8, plus 2 would be 5.8. That's our first estimate. Second estimate would be M4, and so each of those intervals still has a width of 1, but then this way we're using the midpoint height. So for this one, we'd be using the height at 0.5, so turn that into a rectangle, and that height is about right at 0.5 for a y value. 1 right here, and then here use the height at 1.5, which is right at 2. Width of 1 again, and then the height at the midpoint here. Estimating that one, I would say that's about 2.3. Say 2.2 wouldn't be a bad guess either. And then 3.5, if we go right up to the midpoint, that's right around, let's say that one's like 2.2, whenever they'll balance each other out. Or you could have estimated that these were each 2.25 and you would have come up with the exact same number. Setting these together, 0.5 plus 2 is 2.5, plus 2.3 is 4.8, and then plus 2.2 comes out to be 7. So this one's actually quite a bit different using the 2 different endpoints, and that's because I think there's such a significant increase right here that the left was severely underestimating what it was supposed to be. Okay, so that was number 1. Number 11 is on the next page. I think there's a graph that we're supposed to be looking at for that. Yeah, so this one, more Riemann sums. And the first thing it asks is which approximation is represented by the shaded rectangles. And if you look, where it's matching up with is the right endpoint. So that's definitely the right Riemann sum that is being shown in the picture for number 11. So that is right estimate would answer the first part of the question. Then it says compute R5 and L5. So we're just getting the rectangles again, just adding them all together. So they all have a width of 1. So what I'm going to do, since the width is all the same, I'm going to put the width of 1 on the outside and then just sum together all of the heights. That's almost just like factoring out a 1. Of course, when it's a 1, you don't really need to do that, but it would be important to know how to do that if the width was ever anything else. Okay, so for the right Riemann sum, this height is about 30 plus, and then height for the second rectangle looks like it's right at 18. Plus this third rectangle right here is at 6, and the fourth rectangle is at 6, and then the fifth rectangle goes up to 30. Okay, so 30 plus 18, 48, plus 6 is 54, plus 6 again is 60, plus 30 is 90. So that is your right estimate. There's no units for either of these. L5, all of the widths are 1, so I'm going to put that out front, and then I'm going to add up all of the left endpoints. So the left endpoint here is also 30, because they have the exact same value right there. Plus, and then from 1 to 2, the left endpoint is actually still 30. That's this one right here. So now this one's a little weird because you're not following the rectangles that are on the page right now. From 2 to 3, you're following the left endpoint of the red graph, and that would be 18. Plus, and then from 3 to 4, you're following the left endpoint of the graph, which is 6. And from 4 to 5, following the left endpoint of the red graph, which is also 6. Okay, so you can see you actually have, they're in different orders, but you've got 30, 30, 18, 6, 6. So you know that in this case, it's going to come out to be the exact same approximation for those two numbers. Okay, so those are all the pictures that we need to see. The next handful are all antiderivatives, some definite, some indefinite. So 19 is definite. So we've got bounds from 0 to pi over 6. And we have sine x times cosine to the 4th of x. So this is going to be a u substitution. The reason we know is because we have something that looks like it's physically nested within another function. So remember, this is cosine raised to the 4th power. So this cosine function is nested within a 4th power function, and then its derivative is in there somewhere. Derivative of cosine is negative sine, but of course with constants we can always just mess around and change them. So the u substitution I'm going to make will be u equals cosine. And so my du will be negative sine x dx. And then I have a sine x dx. To replace that, I just move the negative over to the other side. So a negative du is going to be used to replace sine x dx. So let's write what we have so far. Leave the bounds off for right now. So sine x dx is going to be replaced by negative du. So I'm going to put the negative out front and then the du at the end. And then cosine to the 4th, cosine is replaced with a u, so I will have u to the 4th as my integrand. And now my bounds. So my bounds in terms of x used to go from 0 to pi over 6. But if I want to change them in terms of u, I'm going to take these bounds and plug it into this equation. So cosine of 0 is the x coordinate at the 0 mark on the unit circle, which would be 1. And then pi over 6 is the x coordinate of the unit circle at pi over 6. And that would be the square root of 3 over 2. Okay, so those are my new bounds. So I'm going to write those in. Cosine of 0, cosine of pi over 6. And then I just jump right into this problem as if this were a brand new problem and this problem never existed. So with definite integration, you never, ever, ever go back to the original variable. By changing the bounds, that was already like plugging the cosine back in. Okay, so we've got this negative outside. The antiderivative of u to the 4th is just a normal power rule. We do 1/5 u to the 5th. There's no plus c if I'm doing definite integration. And these are my bounds. It's not going to be the prettiest, but so I have negative 1/5, sub in this square root of 3/2, raise that to the 5th power, and then minus negative 1/5 times 1 to the 5th. There's not going to be a whole lot of pretty things that I can do with this. I have this negative 1/5 right here. I am going to first raise this to the 5th power. So this is super weird. The square root of 3, if I square that, I get 9. So if I square it, I get 3. So if I raise it to the 4th power, I get 9. And then there's still this extra 1 power of the square root of 3. 2 to the 5th is 32. And then this is just a 1/5 here, because of course 1 to the 5th is just 5. I'm not going to take that much farther. This is going to be an ugly number no matter what. So if you wanted to, you could actually distribute this. I'll have a negative 9 root 3, and then 5 times 32 is what, 160. So there's not much of a point in taking that all that much further. You always do, though, want an exact answer versus a decimal approximation. So remember here, like this right here, if I were to replace u with cosine x and then plug the original bounds back in, this right here is the cosine of my old bound. So by changing the bounds, I've already taken care of plugging the cosine x back in, so you do not do it again. All right, so that's number 19. Next on the list is 31, and these next couple are just indefinite integration, so a couple little substitutions. Okay, so this, remember, you're always looking for something that's physically nested within another function. So that would be this expression right here. And you want its derivative to be in there, or at least a constant multiple of its derivative. So the derivative of this expression is just 10, and that is just a constant. So you can always manipulate that. So my u substitution is going to be 10t minus 7. The derivative of u would just be a 10 dt. I don't have a 10 in there anywhere, so I just want to replace the dt. And I will replace that with 1/10 du. So swap this back out. The 10t minus 7 is now a u raised to the 14th power. dt is going to be replaced with a 1/10 du, and then you just go through and take the antiderivative. So the 1/10 hovers out front. The antiderivative using a power rule would be 1/15 u to the 15th, and make sure you've got your plus c for indefinite integration. And now I'm going to simplify and sub the expression back in. So this will be 1 over 150, and I'm subbing this expression back in for u raised to the 15th power, and then plus c. So that would be my final answer for number 31. All right, next integral was number 35. That's back to being a definite integral. Okay, so we have from 0 to 5, we've got a 15x, and then the square root of x plus 4. Okay, so remember, look for something that's physically nested within another function. So that would be the one that's nested within the square root function. So I'm going to start off with this. And then the du is just a 1, so it's an even swap out du for dx. It's definite integration, so you want to make sure you change your bounds as well. So in terms of x, my bounds went from 0 to 5. So in terms of u, I'm going to take 0 and 5 and plug them into this expression. So 0 plus 4 means my lower bound is 4. 5 plus 4 means my upper bound is 9. Now, these ones are tricky because if you take a look at everything that got swapped out, I'm going to take this 15 and just push it out front like I can do with any constant. 0 to 5 now changed from 4 to 9. And when you start swapping things out, there's nothing to swap out this x. Okay, so it's a rare scenario, but if it ever happens, there's an extra x that does not swap out as part of this, then you have to rearrange your original equation. So according to this, x is equal to u minus 4. So that's what I'm going to do, is replace this x with the expression u minus 4, and then the square root of x plus 4 is now the square root of u, and I'm going to write that as u to the 1/2. And remember, according to this, dx and du just do a perfect 1-for-1 swap. So I can write it like that. It looks like this is still a pretty complicated integrand, but I can actually distribute the u to the 1/2. So let me rewrite this. So distribute u to the 1/2. I have u to the 3/2 minus 4u to the 1/2. And this is now just power rules that I can do with this. So 15 stays out front. Oops, I don't need that anymore, sorry. Power rule says that my power pops up to 5/2, and I divide by 5/2. Minus this one, my power pops up to 3/2. I divide by 3/2, but remember there was a 4 there already. So I would have the reciprocal of 3/2, which is 2/3, times the 4 that was already there. And this is being evaluated from 4 to 9. So remember, with definite integration, you do not sub the x plus 4 back in. You already did that by subbing in the x plus 4 right there. Okay, so simplify everything up. So 15 times 2/5 would be 6. So I have 6u to the 5/2 minus, and then 15 times 8/3 would be 40. U to the 3/2, and I'm evaluating that whole expression from 4 to 9. So first plug in the 9. Make sure you're careful with your signs, with your subtraction. Then plug in the 4. Okay, start with the exponent. So 9 to the 5/2 would be the square root of 9, which is 3, and then raised to the 5th power, which is 343. I'm probably going to break out a calculator in a second. And then the square root of 9 is 3, raised to the 3rd power, which is 27, minus, same thing here, square root of 4 is 2, 2 to the 5th power is 32. And then square root of 4 is 2, 2 to the 3rd power is 8. So I am going to plug this into a calculator. I'm sorry, sorry about that. That's 243, not 343. Okay, 6 times 243 minus 40 times 27 minus 6 times 32 minus 40 times 8, that second section in parentheses, and we end up with a lovely 506 for number 35. Okay, next is 47. Okay, 47, back to indefinite. We have x to the 2nd, x to the 3rd, dx. So remember, with substitution, you are looking for something that's physically nested, who also has a derivative that's present. So the x cubed is physically nested within the exponential function, and its derivative is 3x squared, which I can manipulate constants. So I replace the x cubed with a u, means my du is 3x squared dx, and I have an x squared dx right here, which I can manipulate the constant to say that 1/3 du is going to replace x squared dx. So sub everything in. So my x squared dx is going to get replaced with a 1/3 du, and my x cubed right here is going to get replaced with a u. So it becomes this very simple integrand. The antiderivative of e to the u is just e to the u. And don't forget your plus c when you're doing indefinite integration. The plus c will be worth a point on the test. So if there's a whole bunch of these, you don't want to lose like 4 or 5 points for forgetting your plus c's. That would be very sad. Final answer, replace the u back with the x cubed, and that would be your final answer for number 47. Okay, next antiderivative is number 51. So I have the integral of e to the negative x over, in parentheses, e to the negative x plus 2, and that quantity is cubed. Okay, so again, I'm going to say it every time, but the trick with substitution is looking for an expression that's physically nested within another expression, and that would be this guy right here. It's nested within the -3rd power function. So I take u equals e to the negative x plus 2, and a lot of people would be tempted to rearrange this for e to the negative x and swap that out, but don't do that. Like, don't jump the gun until you see what your du is, because almost every time anything extra will get swapped out as part of your du. So the derivative here requires a little mini chain rule. Derivative of e to the negative x would be e to the negative x times the derivative of negative x, which would be a -1, and then I have my dx. So this guy right here, e to the negative x dx, is what gets swapped out. I just have to move my negative over to the other side, and that's going to be just an easy swap out. So don't try to replace this e to the negative x too early, because it does end up getting swapped out here. So e to the negative x dx is getting swapped out by a negative du. And then this expression is a u, and I can write it as u to the -3rd power, and then just turn it into a simple power rule. So I have a negative on the outside. My power goes up 1 to -2, and then I divide by my new power to be plus c. So I'm going to change this to a positive, so it is 1/2 u to the -2nd power. So I'm going to write it as 1 over 2u squared, because this 2 would be in the denominator, and then the -2nd puts it in the denominator, plus c. And then final answer, I want to make sure that my expression ends up right back where it's supposed to be, because it's, oops, not cubed, squared, because it's indefinite integration. So I should have my original variable back in and a plus c whenever you have indefinite integration. All right, 59 here. Antiderivative, they put the dx in the numerator. We talked about how we don't necessarily love that, so I'm going to put it on the outside here. Okay. This one is not an ordinary u substitution. This one's going to be an inverse trig. The reason you know is because you have something in the denominator. So say you were going to do a u substitution, the derivative of this would be an 8x, and there's no x in here anywhere to swap out. So if it seems like it might be a u substitution, but you don't have a du that you can swap out, then it's not a u substitution, and it's going to be one of the inverse trig, especially if you have a quadratic expression in the denominator. So it's going to end up being inverse trig. So just a little side note here. Here's what we're trying to turn it into. If we can turn it into this, then we know that this will be our antiderivatives. This is the goal, is we want this to become this. So the first thing we need to take care of is if there's anything other than a 1 right here, we need to factor it out, because this has to be a 1 in our formula. So I'm going to factor a 9 out of the denominator. Okay, so now I have a 1, which is a good first step. I'm going to move this 9 just out front. So I'll have a 1/9 out front, because remember, it did come from the denominator, so it's not just a 9, it's a 1/9. So now I'm here. Next move is that this right here is supposed to be a u squared in my formula. So that's going to lead me into my substitution. So I know that u squared is supposed to be 4/9 x squared, and I can simplify it up by taking the square root. So u would be a 2/3 x. And that means that my du would be the derivative of this, and since it's linear, it's just 2/3 dx. And I don't have a 2/3 in there anywhere. I need to get the dx alone, so I'm going to multiply by the reciprocal, and that will tell me what I can swap out for my dx. Okay, so let's make all these substitutions. So I had the 1/9 out front already. I have 1 over This 4/9 x squared is going to be replaced with a u squared. This is already a +1, so that was fine. And then my dx, according to this, is going to get swapped with a 3/2 du. And remember, any constants can just go out front. Variables can't. There's been a lot of misconception with that, but only numbers, constants, can go out front like this. So simplify this up. I will end up with 3/18, which is 1/6. And then the antiderivative of this is a tangent inverse of u plus c. Always make sure for your final answer that the original ends up back in place. So u should be a 2/3 x plus c. So this would be your final antiderivative for number 59.